Well, good afternoon, class. This is Dr. Harn. As a reminder, I'm out of town today on the 9th of Thursday, and so I've recorded this video lecture in place of that in-class time. So a few other reminders. We've got our homework 6 due on Tuesday the 14th in class. And I will hold a special office hours due to missing office hours this week. I will hold these office hours on Monday, the 13th of November, from 8 to 10 a.m. So feel free to stop by and ask your questions about whatever you may wish to discuss, or just stop by and discuss. So feel free to take advantage of these office hour opportunities. So previously we investigated problems of sound transmission through partitions. But today what we'll cover is a new extension to this concept, where we will denote the difference via the term. Now we're looking at transmission through panels, where we define a panel using our term here to be a flexible partition that may vibrate due to incident acoustic waves. So our section today will be on sound transmission through panels. So the general characteristics of sound transmission through panels in terms of transmission loss can be sketched out in a few regimes of frequency. So the sound transmission frequency dependence of panels is typically of this form. So if we plot out this frequency dependence of transmission loss in dB and frequency, we generally have this type of behavior shown here. Now, there are several defining features on this plot, and we'll denote a few distinct sections. So this frequency here is the fundamental frequency. associated with resonance. Vibrations, I should clarify that. So that the transmission loss at frequencies below the fundamental is what we would call stiffness controlled. It's associated with the panel stiffness. Now at high frequencies, there's another dip. And this is the coincidence frequency, giving rise to this kind of diminished area that can be denoted as the coincidence region. And above the coincidence frequency, this transmission loss is mostly damping controlled. So it's controlled largely by the damping characteristics of that flexible partition or panel. Now, in between the stiffness and damping controlled regions, you may suggest that we have a mass controlled region. Indeed we do. This is largely governed by the mass law. Now, I've drawn the slope in the mass controlled region and the slope in the damping controlled region for certain differently for good reason, because in the mass controlled region the rate of change is around 6 decibels per octave, or we recall that an octave is a doubling of frequency. This contrasts with the slope in the damping controlled region, which was around 9 decibels per octave. So what we will cover today will explain and define all of these characteristics that we see here, explaining where 6 decibels comes from, explaining coincidence, and so on. So that's our investigation today. So to begin, to introduce these dependencies of transmission loss, we need to characterize the panel. So we make a few assumptions. We assume infinite span-wise dimensions. So in other words, if we have a panel and it has thickness h, then the other dimensions extend infinitely in height and in width. So in practice, this just means span-wise dimensions, so span-wise dims, are much greater than the acoustic wavelength that we're considering in a specific problem. Okay. With that assumption clarified, our surface density of the panel will be denoted as lowercase m. Not to be confused with an actual mass, but it's a surface density with units kilograms per meter squared. And this would come from a formula for the surface density to be the volumetric density multiplied by the thickness. So volumetric density is our conventional rho term. So this panel will support wave propagation. It's a little bit outside the scope of our course, but waves will propagate in the span-wise directions. And they will propagate at a speed called the bending wave speed that we introduce here using C sub b as our notation. So C sub b is computed from the fourth of the bending stiffness, capital D, multiplied by the angular frequency squared, and then that divided by the surface density. So to write out what I just spoke, the bending stiffness D is equal to the Young's modulus times the second moment of area, I prime, divided by 1 minus nu squared, which is nu is the Poisson ratio. The units of bending stiffness are kilograms meters squared per second squared. And writing out these characteristics, once again, we have that y is the Young's modulus. Pascals or newtons per meter squared. Nu, which is dimensionless, because it's the Poisson's ratio. And I prime, which is the second moment of area, having meters cubed as its units. So for a panel of thickness h, I prime is h cubed on 12. So knowing a bending wave speed, we can define a bending wavelength. As lambda b is Cb on whatever the frequency in hertz is that we're considering. So when this bending wavelength equals the acoustic wavelength, we have a critical frequency that we can define. Which is denoted by c squared on 2 pi times root of m on d. The surface density divided by the bending stiffness. So what is this critical frequency? Well, the critical frequency occurs when the acoustic wavelength and bending wavelength are the same. So this results in efficient wave energy transfer from the air to the panel. And since we very often presume that the panel has air on the other side or opposite side, this means that we have low transmission loss around F sub C. Now, F sub C is not explicitly found on our typical transmission loss plot that we showed. I described something called coincidence. So let's relate coincidence to the critical frequency. And this comes about because waves may arrive at the panel at oblique angles. So we may have our panel looking down now, and we may have a wave front that propagates and impinges on the panel with an angle of theta. So when waves arrive at the panel with oblique angle theta, we need to introduce something called the bending impedance to characterize the influence of that angle of incidence. We've used Z before to denote impedance, so we'll use it again without any special subscripts. So the bending impedance is complex, as it was before, and it's J, the imaginary number, times 2 pi F, the frequency in hertz, times M, the surface density, and then times a collection of terms here in the brackets. We will have 1 minus the quantity frequency on critical frequency squared times 1 plus J times eta, I'll describe that in a moment, times sine to the power 4 of the oblique angle, and then close that bracket. Eta is the panel loss factor. It is dimensionless, and it characterizes the damping of the panel. Or it characterizes damping of panel. Often eta is 0.1 or smaller. So through a sequence of derivations which are beyond the scope of this course, it can be shown that the transmission coefficient is related to the bending impedance according to the following expression. Tau, the transmission coefficient, is equal to the amplitude of 1 plus the bending impedance, capital Z, times cosine of the oblique angle theta divided by 2 rho naught C. This whole expression is, the modulus is to the power -2. Now rho naught C is the plane wave impedance of the acoustic fluid. And we've seen this several times before as well. So when it's air, it's approximately 418, at least at room temperature and around sea level. And once we have computed this transmission coefficient, well, we're able then to relate this to the transmission loss through the standard expression. The transmission loss is -10 times log 10 of the transmission coefficient. By substitution, we find that the transmission loss is 20 log 10 of the term that's in the modulus of 1 plus the bending impedance times cosine theta onto rho naught C, where I've pulled out the power -2 to simplify this expression. Alright, now this term will simplify still further considering our bending impedance equation up here for several cases, and one very important one. So let's consider normal incidence acoustic waves. Such that the oblique angle is 0. And assume that our loss factor is much less than 1. We could simplify this and we'll find that the normal incidence transmission loss can be expressed as 10 log 10 of the quantity 1 plus omega times surface density divided by 2 rho naught C, square that and close your brackets. This equation is very important in acoustics and is denoted as the mass law. So let's investigate the influence of the mass law. So recall that surface density m is the volumetric density times the thickness. So let's consider that we double the thickness. What happens to the TL, the normal incidence transmission loss by the mass law? Well, we could run this here in MATLAB. I have to move things around here in order to get this on the screen. Okay, so let's double our thickness, so we'll have 10 log 10, 1 plus, doesn't matter what we'll use here, so we'll do 1, well, let me be specific, 1, okay, throwing in some numbers there for completeness. We'll have omega times rho times 2 times h, and let's call our h 1, divided by 2 divided by rho naught c. And let's subtract that from the original, or we don't double that and make that instead just 1. And so our change in the transmission loss is found to increase by 6 decibels. So doubling the thickness of the panel in the mass-controlled region, which doubles the mass, increases the transmission loss by 6 decibels. Now, what if we cut this in half? How then does that change our transmission loss? Well, we can come back here to MATLAB again and bring up the same thing and say 1/2, and we have a -6, so the TL reduces by 6 decibels. So we can take this one step further and say, what if the frequency doubles or is reduced by half? A similar result will occur. So I'm going to take this back out of the screen. So 2x f will increase the TL by 6 dB, while a 1/2 x f reduces the transmission loss by 6 dB. So this is why in our sketch of the transmission loss from before, the slope in the frequency axis is 6 decibels per octave, which is either 1/2 or 2x change in the frequency. Now, in terms of what we have found for the thickness doubling, that means that the transmission loss in that frequency regime would uniformly move up for doubling the thickness by 6 dB, or uniformly go down by 6 dB if we cut the thickness in half. So that's the role of the thickness and frequency, or rather the mass, in that mass-controlled region of transmission loss for panels. Now, what about the limitations to this derivation at high frequencies? Because we see that at some point this mass-controlled region terminates in coincidence phenomena. So at high frequencies, the mass law is bounded by coincidence phenomena at high frequencies. What is found is that for frequencies greater than the critical frequencies, there is an oblique angle theta such that the wavelength of the acoustic fluid may be equal to the bending wavelength. And we need to clarify the bending wavelength is a property of the panel and is not dependent upon the acoustics. According to our expression of the bending wave speed from before. So what do we mean by this? A schematic of the situation is very helpful. So let me bring that. This is in figure 66 of the course notes. If we have a wave front that's impinging upon a panel, that has an acoustic wavelength of lambda, and it arrives at this oblique angle theta. Now the projection of this wavelength on the panel may correspond to the bending wavelength. As such, we have that special case that we described. So when the angle gets smaller, figure 66 in your notes shows that this would correspond to a different acoustic wavelength projected upon the panel. And keeping in mind that this wavelength does not change, the bending wavelength, because it is inherent to the structure itself. So, putting this into math, we can find we can then derive a coincidence frequency given by c squared on 2 pi sine squared theta, the oblique angle, multiplied by the root of the surface density on the bending stiffness. And this coincidence frequency is related to the critical frequency by the fact that the critical frequency, this should be f sub b, the critical frequency f sub c is the lowest coincidence frequency at which bending and acoustic wavelengths wavelength projection are the same. And this occurs for the oblique angle being 90 degrees, which is called grazing incidence. So like the case of lost it in my notes there. Like the case of the critical frequency itself, when coincidence occurs, there is an effective wave energy transfer from air to the panel, and if it's bounded by air on the other side, then from the panel to that other air. So this means we have low transmission loss around coincidence. Specifically the coincidence frequency region, which is what we drew before in our sketch of the transmission loss. So after this increase in the transmission loss of the panel by about 6 decibels per octave, at some point the frequency will increase greatly enough that, depending upon this angle of oblique incidence, theta, a reduction of the transmission loss will occur around the coincidence frequency, and above that frequency region of coincidence, we have a growth of transmission loss somewhere around 9 decibels per octave, which is damping controlled. So that's the high frequency end of the transmission loss trend for panels. What about the low frequency regime? Well, the lower frequency at which the mass law trends occur is bound by structural resonances. Associated with finiteness, or the finite panel dimensions. So this is where the panel acts like a finite structure. So we introduce the fundamental frequency to characterize this bounding frequency range. Where that fundamental frequency is computed to be pi on 2 times the bending stiffness on the surface density, and take a root of that, and then multiply by a bracketed term of a quantity a to the power of -2 plus b to the power of -2, where this whole frequency is of course in hertz, and a and b are span-wise dimensions of the panel, the actual dimensions that are of interest. So sketching this out, if we have that original thickness, h, and a and b can be noted as the height and width of the panel. So this type of resonant vibration means that the panel, given its finite size, at very low frequencies will oscillate like the structure that it really is. So it will have vibrations back and forth. So I'm kind of sketching out the displacement profile of the panel surface. At one side of the resonant oscillation, and then at the other side of that resonant oscillation, we have something like that. panel is oscillating like a bulk structure. And I encourage you to enroll in ME 5134 for further details on such structural vibrations. So, let's review. We've seen that the transmission loss in some mid-frequency region is governed by the mass law. The rate of change in frequency per octave is 6 decibels. And if we double the thickness of the panel, that flexible panel will increase uniformly its transmission loss in this region by 6 decibels. Six decibel increase for thickness mass doubling. Then, these trends terminate at high frequencies due to coincidence. That can be identified for a given oblique angle of arrival of waves at a coincidence frequency. Above this region, we have a 9 decibel per octave increase in the transmission loss. That's associated with damping. And you can investigate this using that bending impedance expression and the full relationship for the transmission coefficient. Now, at the other side of this, we have structural vibrations and resonances that prevent this mass law trend from going on ad infinitum down to lower and lower frequencies. And because in fact, at some point, very much of the incident wave energy is propagated through, so the TL is very low when we have resonance. But below that frequency region, we're basically stiffness controlled, and in fact, transmission loss grows, but not ultimately infinitely. It grows to a finite value, because we of course know the wavelengths are so long in this region that base frequencies, long wavelengths, are not ultimately prevented from passing. But this in general is the transmission loss of panels. And we've seen all of these dependencies today. And what we'll look at our next class are several applications of this to context of room acoustics, where we need to design panels to meet certain criteria associated with different frequency regimes. And with that, I'll conclude, and I look forward to seeing you in our next class on Tuesday the 14th. Have a good day.